All right, let's get started with lesson 2, part 2 of historical models of the atom. Now, in part 1, we've talked about Democritus, and remember Democritus developed a model of the atom. The atoms were solid, and they came in different sizes and shapes. All right, we looked at that. And then we looked at John Dalton's model, and he said that atoms were spherical, but they were solid and could not be divided into smaller particles at all. And then we looked at J.J. Thomson's experiment and his discovery of the electron, which resulted in a brand new model called the plum pudding model. And in Thomson's plum pudding model, the atom is still spherical. I can do a little bit better job with that spherical there. It's spherical, and embedded in that model is going to be small little particles that are randomly distributed, that are negatively charged electrons. Surrounding those negatively charged electrons is a positive matrix or cakey-like pudding, all right, which is why I call it the plum pudding model. But what's significant about the plum pudding model is now, for the first time, we're saying that the atom can be divided into smaller particles, known as subatomic particles, namely electrons. Eventually, the proton and the neutron will also be discovered. All right, so let's continue our journey. And now we're going to go to Ernest Rutherford. Now, Ernest Rutherford is going to be a student of J.J. Thomson. And Rutherford is very excited at the time of looking at this new idea of radiation. Now, radiation at the time is thought to be something emitted by atoms. They're not exactly sure completely what radiation is, just that it's coming from atoms. So Ernest Rutherford is also not only interested in this new idea of radiation, but proving J.J. Thomson's plum pudding model. And so Rutherford is going to put together another experiment that becomes very important. And this experiment is going to, again, change our model of the atom into a brand new model. All right, so before we get to the Rutherford model of the atom, we're going to look at Rutherford's experiment first and how the results helped us to change into a new model. So let's turn to our notes to Rutherford's experiment, and this is going to be on page 12. Rutherford's experiment is going to be known as the gold foil experiment. It's simply set up this way. He has a box of lead that is going to be surrounded by a radioactive source material, okay? So this material is radioactive. And what it's going to do is shoot out radiation. Now, the type of radiation that is being shot out from the source are known as alpha particles. Okay, now, at the time, Rutherford did not know what an alpha particle really was, but he did know a little bit about it. One is he knew that it was fairly large. All right, not as large as an atom, but much larger than an electron. He also knew that alpha particles were positive, and this is important. So alpha particles were large, positively charged. All right? But that's about all he knew and understood about these particles at the time, other than the fact that they were being emitted from atoms. So he was very interested in these alpha particles, and he was wondering if these alpha particles could help him prove J.J. Thomson's plum pudding model. So what he did is he got a very thin piece of gold foil, and he surrounded the gold foil by a screen, which is represented by here. The idea is that the alpha particles would go through the gold foil and hit the screen. Now, the screen is going to act like photographic paper, where when the alpha particles hit it and the paper is developed, it should show where the alpha particles hit on the screen. Right? Now, what Rutherford believed would happen is this. If the plum pudding model was correct, we're going to make atoms that are spherical that represent the atoms in that gold foil. Now, if electrons were distributed randomly, we'll just put electrons being distributed randomly in these. Each of these atoms is made up of different amount of electrons. Okay? What he believed is that the alpha particles would go directly through, straight through the atom. Okay? Just right through. Okay? That's what he believed would happen. However, the results were quite different. Okay? So let's again make our atoms. All right? They didn't go directly through all of them. Okay? There were many that did. It went right through the atom in a straight line. But there were some others that were actually being deflected at different angles, and some even deflected backwards, like so. All right? So this is not what Rutherford expected to occur at all. Right? Now, because these alpha particles were being deflected at different angles, Rutherford immediately knew something was wrong with J.J. Thomson's plum pudding model. Now, he was a smart man, and because of his genius, he recognized what was really occurring here. All right? So if we go back and look at the representation of his experiment, you can see that a lot of the alpha particles were going straight through, but some of them were being deflected at different angles. Okay? What could this mean about the atom? This is what Rutherford theorized, right, in our boxes. What Rutherford really believed was that J.J. Thomson's ooze or matrix of positive charge is incorrect. What he now discovered was that the positive charge was located in the center of the atom. Right? All the positive charge is in that center. And he's going to call that center positive charge, he's going to call it the nucleus of the atom. And what is happening is that nucleus is not bigger than the actual atom, but it's quite massive compared to the electron. So what's happening is that when those alpha particles, which are positively charged, right? So those alpha particles, most of them are going straight through, the majority of them, like he predicted. But what will happen is that because the alpha particles are positive, when they get next to that positive nucleus, positive and positive are going to repel. And so since those nucleuses are so big and so positive, they're going to literally cause the alpha particles to deflect at a different angle. So again, as it gets close, it deflects at a different angle. If they hit almost head on, it's going to cause it reflecting right back. All right? Essentially, what the gold foil experiment does is discover the nucleus of the atom. And not only discovers the nucleus of the atom, but it discovers that the nucleus contains all the positive charge that is found in the atom that offsets the electron. So essentially, this is the results of the gold foil experiment, and this is what we learned from the atom. One is that the nucleus is now positive and located in the center of the atom, so you should probably write that in. Two, that most of the mass of the atom is located in the nucleus. The nucleus, therefore, is very small but very dense. All right, small and compared to the overall size of the atom. However, the nucleus is quite large compared to the electron. The electron is super, super, super tiny. All right. The atom, therefore, is mainly empty space. And the electrons, again, are very tiny compared to the nucleus. All right, so these are the conclusions that Rutherford is going to make about the atom according to his experiment that was done. So this is going to have to change our whole idea of what the atom now looks like. And we're going to have to build a new model. Now the model that Rutherford is going to make is typically called the Rutherford model. So let's draw it. Essentially, Rutherford is going to say that the atom is made up of a positive charged nucleus, that the electron is going to move around that nucleus in specific paths, and he didn't know exactly how, but something like this. And you're familiar, or probably seen, the atom drawn like this. Now these orbits around the nucleus are where the electrons are. We're going to use the symbol E for electron, and of course it's negatively charged. So this is simply Rutherford's model, okay, of the atom. However, Rutherford understood and recognized that there was a problem to his model, and that is this. Rutherford understood that the electron, being a negatively charged particle, is going to be in motion. And if it is moving, it is going to emit energy. And if it emits energy, that means it's losing energy. And eventually, the electron should essentially crash right into the nucleus and annihilate the atom. So he felt like he was onto something, that he knew that the nucleus was positive, that it was really there, that it actually existed. But the problem was the motion of the electron. He just could not rectify the fact that the electron then would be moving around the nucleus and eventually would lose energy and crash into it. And so it wasn't until much later that the answer to this problem is going to be discovered. All right, soon after Rutherford's model of the atom, eventually the neutron is going to be discovered. And the neutron is going to be discovered by Chadwick. And so Chadwick's discovery of the neutron is going to then further our understanding of the nucleus. We now know that the atom is composed of the positive charge, which is now called the proton, and also, not the electron, the proton, and also another particle that has no charge, which is known as, I'm writing this in the wrong place. The proton, and another particle that has no charge, that is known as the neutron. that is found in the nucleus. Okay. So now we have to solve this problem of the electron crashing into the nucleus. Now, this is going to be rectified by a man named Niels Bohr. Niels Bohr is going to come along around 1913, 1920s, and is going to develop a new model. This is going to be known as the Bohr model or the shell model. Now, this new model is going to come around about because of what is introduced as the quantum theory. All right? Now, we're going to spend a lot more time talking about the quantum theory and what it is. So I'm briefly just going to mention what Niels Bohr or the Bohr model is, or the shell model. Essentially, what Bohr is going to do is he is going to place the nucleus still in the center, like a Rutherford model, and it's going to be positively charged. But now the electrons are going to be in specific orbits around the nucleus. This is kind of terrible, isn't it? Let me make it smaller. So positive charge, but we have electrons that are going to be found in specific orbits, kind of like planets. And so sometimes we call the Bohr model not only the shell model, but the planetary model, because it is thought of as that electrons are going to be in orbits that are going to move around the nucleus. The only difference is that electrons can only be at these specific distances. It can be this far or it can be this far, and it can never be in between orbits, okay? Never exist between those orbits. And because of that, the electron can never crash into the nucleus, all right? We'll get into a lot more specifics about Bohr model a little bit later on, but that's to get you started, all right? Now, the Bohr model itself starts helping us to get even closer to our current model of the atom, all right? There is mistakes in the Bohr model that we'll address later, all right? For now, what we're going to do is get into what we call the electron cloud model. Sometimes this is known as the quantum model of the atom. The electron cloud model is our current model of the atom. It is essentially going to be drawn or look like this, that the protons are in the nucleus with the neutrons, but the electrons are not in specific orbits. Instead, they are found in clouds. I'm going to draw a cloud for you. And these clouds are around the nucleus of the atom. And the idea of a cloud is to suggest that electrons can be anywhere within the cloud. All right? Electron can be anywhere within this cloud. But the idea is that we don't know specifically where it is, just somewhere within this cloud. In other words, it's based on the probability where an electron would be located at, okay? That's kind of what the cloud model is based on, is the quantum theory of the atom, which we'll discuss later, and the idea of the uncertainty principle, that we can know only the energy that an electron has, but never its true location. It's just somewhere within this electron cloud, okay? So I'm not going to go any more detail than that with the electron cloud model until later on. But at least you're kind of seeing this historical look of the development of the atom and the models of the atom. Now, what can we learn from this? What can we gain from this other than understanding what we believe the atom looks like and how it behaves. Well, what we can learn is that over time, models, which are theories, do change. And our understanding of models change due to the development from new scientific discoveries and experiments. And so today, even though we have what is called the electron cloud model, over time, new experiments could lead to a better understanding or even a new model of the atom. And so we can never say for certain we have discovered the correct model or the correct idea of what the atom is. All right? And so that's the takeaway of this whole lesson. All right? So that is it for now.